Alright guys, today I'm gonna show you a simple trick that makes your simulation more readable and easier to understand. This trick is something I learned during my career as a FPG design engineer. And as the FPG design engineer, you have to read a lot of simulation, which is always the case. And the waveform is the essential part of the simulation. From the waveforms, you get to know where there is any problems within your logic, and from that on, you can debug into your RTL code and find potential errors. Okay, so let me demonstrate to you the module we're gonna examine today. So I precompiled a simple module which is a three-stage synchronizer, and here is the code. As you can see, it's like a dual flop, but it has one more stage. So you can see that there's three internal registers, and each register's value is passed by the value of the previous register, which is like a chain of flip flops. Excuse me. Okay, and about the test bench, which is also pretty straightforward. Here we have a initializer, basically initializing the clock initial value and the reset initial value. And this is the clock generator. Since GTK wave has some limitations, I cannot really put in a forever block here, so I put a for block here. But the purpose is the same. We just generate the clock signal. As you can see, the clock signal toggles every 5 seconds, meaning we have a clock cycle of 10 nanosecond. Remember, I put a time scale here, so everything is in nanoseconds. And here we instantiate the module we have. This initial block specifies how the input signal changes. So basically, after 50 nanoseconds, the reset is deasserted, and from after 100 nanoseconds from the very beginning, the input signal D begins to change, and it toggles every one clock cycle. Okay, now let's take a look at the waveform first. Alright, so we first compile using the iverilog command. -O specifies the output file. We give it a dump, and we are gonna add in our module. Alright, since I've pre-checked there is no errors, then we pull out the waveform. VVP dump. Okay, now let's open up the GUI. Sync wave.vcd. Okay, let's pull out the signals from the test bench, or we can just view the signals of the DOT. We select every input and output as well as the internal signals. Click on yes. Alright, everything goes as planned. So okay, actually there is a little bit of issue here. So the clock signal should be toggling from the very beginning. Uh, it doesn't really matter, but let's just see the signals here. So as you can see, at this 110 nanosecond, sorry, 100 second nanosecond, the input signal goes from 0 to 1. And at this clock edge, positive clock edge, the signal, sorry, okay. So the signal gets sampled, and the first register R0 goes from 0 to 1. Since it's a positive edge sensitive, the signal toggles only at the positive edge of the clock. And then register 1 goes high. And then register 2 goes high. So it's a three-stage synchronizer. And the output is a wire attached to the third register. Okay, so the simulation looks good, but let's take a look at take a look at the signals a little bit closer. So when I first started as a entry-level engineer, I wasn't too familiar with the how a register works, how the signals looks like whenever there's a clock. I was kind of confused, particularly at this part. You see here R1's value becomes 1 and R0's value becomes 0. We know that R1 is also clock edge sensitive, right? The reason it becomes 1 is that because the input of the R1 is 1, which is why it transitioned from 0 to 1. But I always questioned, look at this. Look at the look at how close these transitions are with each other. I always question whether R0 meet the hold requirement for R1. We know that for a digital circuit there is setup and hold requirement. So hold says that after the clock edge, the signal has to retain its value for some time before it can change in order to avoid metastability. But here it seems that the signal changes its value right after the clock edge. Of course, it doesn't meet the hold requirement, right? So usually, when you take a look at the datasheet of a register, the hold time should be around, like say, zero point 0.3 nanoseconds, given a specific technology, right? So, since this is just simulation, right, and everything is too ideal, but in reality, there is requirements. There's timing requirements, setup and hold. So how do we make this issue? I mean, how do we make this simulation looks as if it meets the timing requirement? For example, the signal meets the hold and setup requirement. Okay, so let me show you a simple trick where you can make your waveform looks completely make sense. Okay, let's close this first. So the trick is I've precompiled another file. Let's pull it out. Sync 0.v. Okay, so the trick is adding a delay parameter. So let me put these two close to each other. You will see the difference. So these two modules are basically the same identical modules, except that the second one I added a delay parameter, which is denoted by this local param keyword and a pound delay. So delay equals to 1, which means that at a clock positive clock edge, this signal does not change until 1 nanosecond later. I mean, all these signals have the same characteristics of 1 nanosecond delay. This is used to mimic the hold requirement, right? So everything else is identical, and I use the same test bench. Also, okay, before I tell you that, let's just look at the waveform first. Okay, let's do our compilation with the new file. Okay, okay, let me just give it another name. Dump zero. GDK wave. Actually, I can use my history. Sync wave.vcd. Alright, let's take a look. Same here. Let's add the signals here. Okay. Now let's zoom in. Alright. So the input changes value at a negative edge, which we don't care because we only care about the positive edge, right? So at this first positive edge, the R0 register samples the value of the input, which is 1. Since we added this 1 nanosecond delay, you see that the value does not change instantaneously, which is, this one mimics a propagation delay. So we know that the real register in life has a propagation delay. This basically emulates that. Now let's look at the R1 register. All right. So at the second positive edge, R1, excuse me, let me zoom in a little bit. Okay, so at this particular clock edge, R1 will transition from 0 to 1. But notice that this R0, which is the input of the R1, retains its value, retains its voltage 1 nanosecond after the clock edge. Now that we don't have this concern anymore that if it meets the hold requirement, because we know that it indeed holds its value for 1 nanosecond. Okay, and the rest is basically the same. It's a three-stage synchronizer. At each single clock edge, we notice that the setup obviously meets the requirement, and the hold meets the requirement. Okay, so this is a pretty good practice with which you can make your waveform more readable and less ambiguity. Well, there's something I have to add though. So you see this, for this keyword and the delay parameters we added here, this has nothing to do with synthesize with the synthesis, which means that adding these parameters does not affect the synthesis at all. So essentially, these two files will synthesize to be the same identical three stage synchronizer without any difference. The only difference is the waveform, the simulation. So just to be clear that these parameters has nothing to do with the synthesis, so that you can rest assured that your circuit, your software may not synthesize your same code into something else, something you don't want, right? Okay, that's it. That's it for today. I hope you guys learned something. Use this practice and be a good RTL designer. Peace.